Hello everyone, welcome to this new video. So in this today's video, we'll be solving the problem largest rectangular submatrix whose sum is equal to 0. Fine. So this is a hard level question and the topic tags of this question are prefix sum, hash, dynamic programming, matrix, data structures, algorithms. To be honest, yes, we'll be using some of this for sure. And before we proceed further, I would like to mention this thing that there is a error in the framing of the question by GFG. I'll also highlight where is the error, and I'm also promising you that if you watch this video completely, okay, from the start to the end, any sort of problems on the similar lines can be easily solved. Okay, so all these questions revolve around the same concept, that is prefix sum. So if you have the clarity about prefix sum, this is a cakewalk for you. It's just that how are you going to implement the further procedure, but the main crux concept will be easily solved, will be easily figured out if you have the clarity about the prefix sum. All right, so this is a hard level question. I accept it partially, but to be honest, I have made it so easy so that people can easily follow it. But only thing is, please make sure you're watching it till the end. Fine, I've taken a lot of cases and I've explained it to the crystal clear in the bottom line approach. So I hope you people will understand that. So this is a very pretty big code, so that's the reason I have already coded it up and I have written it here before, like without just coding in the live. Okay, so let us go to the question now. Given a matrix mat of size n by m, the task is to find the largest rectangular submatrix by area whose sum is equal to 0. Fine, so you need to find that largest largest rectangular submatrix whose area is maximum and also the sum is equal to 0. So there might be various submatrices whose sum is equal to 0, the overall sum. So overall sum in the sense all the elements in that particular submatrix can be the sum of the all the elements in that particular submatrix can be 0, but there might be various submatrices like this. So choose the one that has the highest area. So highest area in the sense number of rows into number of columns gives you that area. So that's basically rectangular area. How do you find the area for rectangle? Length into breadth, the same thing apply here. So length is equal to number of rows, width is equal to number of columns. That's it. So if there are multiple solutions, return the rectangle which starts from the minimum column index. Okay, so there might be a case with same area. So let us assume 10 is the 10 units is the maximum area that you found, and there are multiple solutions starting with that are having 10 area 10 units as the area, 10 square units as the area. So take that solution which starting from the minimum column index. And second one, if you still have multiple solutions, return the one starting from minimum row index. This is where the error comes up from GFG. So this is different. I mean this is this is the third preference actually. So I list it out. So this must be coming after this particular statement. What is the third statement? If you still have multiple solutions, return the one having greatest row number. So this is this particular thing, like greatest row number has been given the second preference according to that GFG. Like if you actually solve this question for various test cases, you'll get an idea of it, because I have solved it, I have submitted it for nearly 16 to 15 times. I've understood that preference is given to, second preference is given to this. First preference is to the column index, minimum column index. Second preference is that is having great row number, greatest row number. Greatest row number in the sense it must be having greater number of rows, that particular solution. And third preference is given to that which is having a starting from the minimum row index. Okay, so if there are two solutions that are starting from the same column index and have the same number of rows in the solution, then go with the one that is actually starting with the minimum row. Okay, I mean the first row. Okay, so that is the thing. This is the second preference. That is the error from the GFG. So I even reported it. Let us see what replies comes from GFG, and these are some of the examples. We'll go through them. And the solution, the particular solution, my solution, the expected time complexity from GFG is O of n into m into m, and auxiliary space is O of n into m. But the solution that I am explaining will be having the same auxiliary space, but the time complexity is O of n into m whole square. Okay, just we are multiplying it another n. So that is how this is also an optimal solution. This is much more optimal, but I feel like that's much more confusing and it's not really necessary according to the constraints that have been given. So that I'm explaining the most optimal and also most comfortable solution. Okay, so let us go through the example now. So this is an example that has been given, n equal to 4 and m equal to 4, and this is a matrix that has been given. So what is the output here? Output is actually equal to -6, -7, 8, 7, -2, 0. Why is that so? So -6, -7, +8, +7, -2, +0. What is this output? So this is actually equal to -13. This is +15, -2. So that's actually equal to 0, isn't it? So the overall output of this particular value submatrix or the rectangle that you have taken comes out to be 0. So this overall stuff is actually coming out to be 0. That is the reason this is the answer, right? So I hope you people have understood. But you might have found various other like submatrices as well, various other possibilities as well. But out of all those, this will be given more preference, right? So if you can find out another submatrix, like I have not figured it out, but I feel this is the only one that is having. But if you have found, if you can find another submatrix in this particular matrix itself whose sum is actually 0, that will be given least preference than this, because of the three conditions. What are those conditions? Like this is an error in the question. This should be the first preference, like less column index. This must be the first preference. So if there are two solutions possible, give the first preference to that solution which is actually starting with the less column index. Okay, and second preference is given to that which is having maximum row number. So there are maximum rows. So for a solution, let us assume there are first solution there are 4 rows, and second solution there are 3 rows. Give preference to this. Give preference to this, provided both are starting from the same column index. Okay, both are let us assume this is starting from 0th column index and this is also starting from 0th column index. Give preference to this particular solution. Okay, so that is the thing. And if in case both of them have the same thing, like both of them start from 0th column, both of them has 4 rows of solution, I mean 4 rows of arrays, and then in that case give preference to that solution which is actually starting with the low row index. Like for example, if this is starting with second row and this is starting with third row, give preference to this. Okay, so that is the thing. But if you rearrange this preference, like if you give second preference to this and third preference to this, then it will be an error. It will be an error. Okay, so it's that is where I failed many times in this particular solution. So I was like giving more preference to this this thing, because in the question it's been given like this is the more preference, but in reality that's not the case according to the test cases that have been given by GFG and expected answer. So please make sure you're making a note of it. Now let us start framing the approach. Okay, so how do you frame the approach? So at anything, so like let us assume this is the array that has been given. Okay, this is the array has been given. So what is the naive brute force approach that you're going to do, right? So you'll be figuring out all the submatrices, right? You'll be figuring out all the submatrices. So you'll be starting from here and then you'll be going to this. You'll be finding all the submatrices involved. So first you'll take this one, and this one, and this one, and then you'll be moving here, and then you'll be taking this these three, like you'll be finding like all the submatrices. You'll be framing all the submatrices of every size, right? Of every size. But aren't you can you notice that you are doing an extra work, right? So when you're actually traversing the whole thing again and again and again, just to make sure you're finding just in a vision of finding many all the submatrices, you're doing the same repetitive work once again, right? You're doing the same repetitive work again and again and again. So to exempt that, we'll be using the concept of prefix sum. So where does this concept come from? Like if an example, there's a popular question like this. So there's an array given, right? There's an array given. So there are some elements like this. So 1, 2, 3, 4, 5, 6, and let us assume there are negative elements as well. So let us assume this is -2, this is -4, and you're asked to find that particular range of that particular subarray whose sum is actually equal to 0. So how do you find it? Take the prefix sum. So if you take the prefix sum of this, the first index would be 1, second index would be -1, third index would be 2, fourth index would be -2, fifth index that is this index would be 3, and this would be 9. So you'll be seeing if at any point two elements are having the same value. Let us assume this, like right now it is not the same value. Let us assume this and this are coming to be same value. That means there is no progression here. There is no difference here. That means the total value in between turns out to be 0. That is the reason same elements appear here and here, right? So how do you calculate the prefix sum? You just add up these things, right? You'll just add up these things. So at any point, this value 9, what does 9 denotes? 9 denotes the sum of all the elements from 0th index to the last index. So 9 denotes that. So isn't it 1 minus 2 minus 1 minus 1 plus 3 2 2 minus 4 minus 2 plus 5 3 plus 6 9. So that is what 9 is. So 9 denotes the sum of all the elements starting the first index till the last index. So what does 3 denotes? 3 denotes the sum of the elements from the first index to this fifth index, right? So that is what it is. So prefix sum actually stores the sum of all the elements till from starting index till the last till the index that you're working on. So same thing, same concept, similar concept you can even apply here. So how am I doing it? So I'll just erase all these things so that it will be free of confusion. So prefix sum, how are you going to do it? So let us take this example, okay? This array, let us take this array, 2D array. So what is a prefix sum? So at this point, like this particular index, this particular grid, okay, this particular grid, that denotes the sum of all the elements, okay? That grid denotes, like this is the original, okay? This is the original. So after modification, after doing the prefix sum algorithm on this particular 2D array, this grid denotes the sum of all the elements starting from the 0th, this particular starting point, that is 0, 0, so 0th row and 0 column till this particular row and column. So this is first row and first column, right? So this particular grid denotes the sum of all the elements starting from 0, 0 till that particular index. So here it is 1 1, so 1 1. So how do you get the prefix sum? You just do the right side first, you just flip this elements, like add the elements that are there. So 1 plus 2 turns out to be 3, 3 plus 4 turns out to be 7. Now put this flip this up, okay, flip this this particular element into this, so that turns out to be 10. So 10 is the final answer. So 10 comes up in this particular position. So what does 10 means? 10 is actually equal to sum of all the elements 1 2 3 4, as you can see, 1 2 3 4, isn't it? So 10 is actually equal to 1 plus 2 plus 3 plus 4. So how are we doing it? First we traverse it to the right side, we put all the elements, so 1 plus 2 plus all the elements, and then we do the bottom. Okay, first we go to the right side and then we go to the bottom, and finally whatever the answer is stored at a particular grid denotes the sum of the elements starting from 0 to 0 to that particular I comma j. Okay, so that is the simple prefix sum algorithm. How you, like, that's how you simply apply it. Okay, so you just apply it, you just go to the right side first and then flip them to the bottom. That's what I've done. I've shown that with the example, basic example of a 2D array. You should have got enough clarity by now. So you just add the previous sum, previous elements, so 1 plus 2 3. Let us assume you have another array, again do the same thing. So horizontally it is done. Now do the vertically as well. Okay, so that will be finally the answer at that particular 10. So 10 denotes the sum of all the elements starting from 0 0 to that particular I comma j. Right now I comma j is 1 comma 1, because this is what we are dealing, right? This is what we are dealing. So 1 comma 1. So this 10 denotes the sum from 0 0 to 1 comma 1, isn't it? So that's a simple thing. So I'll just erase all these things again. Now let us assume that I am extending it to 3 by 3. Okay, so I'm extending it to 3 by 3, and now I'm interested in finding the sum of the submatrix of this particular thing. Okay, so this whole submatrix, I'm interested in finding the sum of this particular submatrix. So how am I going to do it? So if we can understand the similar prefix sum algorithm, if we can just extend it. Okay, so what does R2C2 denotes? Prefix of R2C2, the sum of all the elements starting from 0 to 0, 0 comma 0 till R2C2, right? So this is what prefix of R2C2 denotes. So that is the reason I've highlighted it with yellow color. So whatever the boundary that I'm actually drawing it with yellow color, that means it includes all those particular elements in that particular boundary. Okay, so prefix of R2C2 denotes the sum of all the elements starting from 0 comma 0 to R2C2. Now I'm just interested in this particular submatrix. So how am I going to get the sum of that particular submatrix? If I just erase the sum of sum of these particular elements and these particular elements, if I just subtract it, and because I'm subtracting one for twice and I'll just add them up, so I'll be getting the sum of the particular this subarray, submatrix, this particular submatrix, I'll be getting it, isn't it? So from the whole prefix of R2C2, which denotes the sum of all the elements, I'll just subtract this particular first row and first column, because when I'm subtracting first row and first column elements, I'm subtracting one for twice. So that's the reason I'll just add it up once again. So if I do that, I'll be getting the sum of this particular submatrix, isn't it? So that is what I'm doing here, right? So prefix of R2C2 denotes the sum of all the elements. Now how do you remove this first row elements? So that is basically this one, right? So if you just remove this, what is this? This is basically prefix of R2 C1 minus 1, isn't it? What is this row? R2. What is this column? Because this is C1, right? R1 C1. So what is this column? C1 minus 1. So that's the reason you'll be removing all the sum of the elements that are there in this particular thing. So this denotes the sum of all these elements, 1 4 sum, isn't it? After doing the prefix sum array, when you do the bottom traversal, you'll be adding up all this like this. So this particular grid denotes, that is prefix of R2 C1 minus 1, denotes all the elements, sum of all the elements in that particular column. And how do you remove this? This is basically this particular thing. So if you'll be aiming to remove this particular first row, so you're done with the first column removal. Now we'll be aiming to remove the first row. So that is prefix of R1 minus 1 C2, right? Because the column is this, you're going to the column C2, you're going to till this particular column, C2 column, but you're starting from C1 minus 1 because this is R1 C1. So this is R1 minus 1, right? So this is the R1 minus 1. So just subtract all the elements. So when you do the right side traversal, you'll be adding up this element, etc. like this. So you'll be just subtracting those particular elements, and finally you'll be adding up this particular grid. So what is this particular grid? This is prefix of R1 minus 1 C1 minus 1, because this is being subtracted for twice. So you just add them up. So this is basically this point, R1 minus 1 C1 minus, because this is R1 C1. So this would be R1 minus 1 C1 minus 1. This denotes the sum till this particular, from starting 0 to 0 to that particular grid. Okay, so once you do it, so if this total thing turns out to be 0, if this particular sum turns out to be 0, yes, then that is what you're actually looking at. That is one of the submatrices that you can consider. So what would be the size of that? That is R2 minus R1 plus 1 into C2 minus 1 C1 plus 1. This is basically length into breadth. That's it. Okay, so this is what you'll be getting the size. Now you'll be giving the preference. So if this particular size comes out to be greater than the initial answer that you have got, so let us assume before you have got a solution and that particular size is less than this particular size. Right now you have got much greater size, you'll be taking this. But let us assume if these both are same sizes, before answer is actually equal to present answer, then give the preference accordingly. If your present column is less than the before column, then take this particular solution. If both of them are starting with the same column index, then go with the maximum row number. If both of them are having the same number of rows involved in the particular solution, go with the solution that is having less row index. Okay, so that is what you're going to do. That's it, very pretty easy. And finally, after you have got a particular submatrix, how do you return it? Take a 2D array. Okay, take a output 2D array, and how many rows will that be? R2 minus R1 plus 1, isn't it? So your final submatrix, you will be putting that in a particular 2D array, and it will be returning it. So how many subarrays, how many rows will that particular 2D array will be? 2D array will be having R2 minus R1 plus 1, and same is the case, column C2 minus C1 plus 1. That's it. So you can now just put each and every element after taking the particular size. So let us assume you have got a submatrix of 3 by 4. So you'll be having your output array will also design like this: 3 rows and 4 columns is what you'll be deciding. So I've drew an extra line. So 3 rows, and you'll be putting each and every element of the submatrix that you have got. You'll just put it, and finally you'll be returning it. Okay. So what is the time and space complexity? Like you're considering every submatrix, so you'll be using 4 for loops. So that turns out to be O of n into m whole square. And after considering a particular submatrix, you'll be evaluating the perfect sum. So in the worst case, it can go up to O of n into m. So the total is happening to be O of n into m square plus O of n into m. That turns out to be just O of n into m whole square. And space complexity, because I'm using an extra prefix array, so I'm going to take some extra space. So for that, O of n into m. Okay. Now let us go through the code. It will be much more easier for you to understand now. So the first part, so I've taken int n and m. So this is rows and columns of the particular array that I've been given, 2D array. And now I've taken a prefix matrix. Okay, prefix 2D matrix. That is the space extra I'm taking. And now I'm doing the right side. This is the right side traversal. Okay, so right side traversal. So I'm just adding up elements. So it's like basically this thing that you're doing. So you're doing this thing, right? So in this 2D array, if you just see, you're doing like this, you're going like this. Okay, so just adding them elements like this. So that's what you're doing. So initially you'll be taking prefix of ij to be a of ij, and if you're starting from the second column, because if you're starting the first column, there's nothing to add to the left. So if you're starting from the second column, so one index column, 1 minus 1 greater than or equal to 0, yes, then there is some column to your left. So you'll be adding that particular things to your okay. I just made an error. What did I do now? So yeah, prefix. Okay, this is prefix, and this turns out to be j minus 1. Yeah, so j minus 1 greater than or equal to 0, right? So this is the right side, and this is bottom. Okay, this is bottom. So after doing this is like this thing that you're doing. So you're going like this and this like this. Okay, you're going down, and you're adding the elements. Okay, so when you're doing that, this is what the formula that you use for int j equal to 0, j less than m, and you'll be seeing that you'll be starting from the first row. First index row. So after all this happening, like you'll be taking int answer to be 0, and submatrix is 4, 0. So what does this submatrix denote? This denotes the starting row, starting column, and end row, end column of the particular submatrix that you're going to take. Take the 4 for loops starting from int r1 equal to 0, r1 less than n, and r2 starts from r1, and c2 starts from c1. So these are the ending row and ending columns. R2 is ending row, c2 is ending column. Okay, so you're taking every possible matrix, and you're storing the elements like the sum in the prefix array. Okay, prefix sum that you have taken, prefix array, instead of traversing again and again and again. Okay, so int sum equal to find sum of r1 c1 r2 c2 nm pref. So what does this function do? So this function is thus: int sum equal to prefix of r2 c2. So if c1 minus 1, so this is the same thing that we have written, this thing. Okay, so this thing. So for each and every r2 c2 we are first taking the whole r2 c2 sum, and from that we are subtracting r2 c1 minus 1, r1 minus 1 c2, and then we are adding the r1 minus 1 c1 minus 1, because it's being subtracted for twice. This particular sum is the sum of that particular array or the submatrix that you have taken. Okay, so that's it. And if this particular sum turns out to be 0, then find the submatrix size. Okay, r2 minus r1 plus c1 1 into c2 minus c1 plus 1. If this particular submatrix size is greater than the answer, like your previous answer, then that answer will be updated with that, and submatrix would be r1 r2 c1 c2. If in case this turned out to be the same answer, okay, then give preference to the column. If your present c1 is less than the initial, so before solution, where did I store? Submatrix, right? Submatrix. So what is the c1? That is submatrix of 2. So that is what I'm comparing. If present c1 is less than, so give preference to the less column index. Then the submatrix of 2, so then update it. Okay, submatrix would be r1 r2 c1 c2, your present solution. Or if in case both of your solutions have same column, okay, same c1, then go with that which is actually having the more number of rows. How do you calculate? R2 minus r1 plus 1, and if that is greater than your previous submatrix of 1 minus submatrix of 0, so submatrix of 1 gives r2, submatrix of 0 gives r1. So if that is greater than the previous one, then also you take the present solution. Or if in case both of them are same number of rows and starting with the same column, give the preference for the one that is starting with the less row index. Okay, so r1, if that is less than the submatrix of 0, give preference to that. So in all these three cases, you are going to take the present solution. Okay, so after finally, if your answer is 0, so what is the answer 0? This initial thing. If you're finally your answer is 0, that means you did not find any submatrix that is actually having the sum to be 0. In that, return the null vector. That's what's being given. If no such matrix is present, return as 0 size matrix. So that's what we are returning. And if in case that's not the case, if in case you have found something, if your answer is not equal to 0, then take the first row submatrix of 0, last row submatrix of 1, first column submatrix of 2, last column submatrix of 3, and just take your answer matrix that to be last row minus 1 minus first row plus 1, like number of rows, and this is number of columns. Initialize all those particular grids with 0. Now start traversing for int I equal to first row till last row and j equal to first column till last column. So answer matrix of I minus first row, right? Because yours, let us assume you have got a 3 by 3 submatrix starting from fourth row and fifth column. So how do you get the answer matrix of answer matrix? You'll be starting from the first 0 0 in the answer matrix, right? So that's the reason I'm subtracting first row and then subtracting first column, but you'll be putting the same values that are there in the fourth like original matrix, right? So if you just manually do it, you'll be getting much more better clarity. And finally return that answer matrix. Okay, so that's the whole thing. I know it's a tedious process, there are a lot of segments, but I made sure that I've explained everything in the bottom line approach, like to the grassroots level. I've made everything pretty crystal clear with the help of examples and all. There might be some audio disturbances in between, but please don't mind them. Please do this on manually, take some matrix and do those things manually. You'll be getting better clarity for sure. I'm aiming that you people will be I'm aiming to make sure you people will be getting this approach and using this particular sort of approach to solve similar line of problems. Okay, it's not like I'm only helping you people for solving this particular problem for today's problem of the day. No, that's not my aim. My aim is to make sure I provide you with such an approach, such an intuition, so that you can use it in solving all the other type of problems in the similar line. Okay, so this is the whole thing. And also the codes in C++, Java, Python are there in the description. Please go through them for your reference. I've attested all of them, and if there are any doubts, please feel free to comment in the comment section. Okay, so that's all for today. So thank you for watching, guys. Stay tuned.